2, 1.
Thank you. So welcome everybody to the final workshop of today, which is on model discovery, concepts, methods, tools and applications. I'm really excited to be presenting this workshop as an organizer alongside Ivan Garibay and Josh Epstein. In terms of the program for today, we've got quite a packed agenda. I'm going to try and keep it to time as well as I'm able to. So we're starting off with a trio of talks, kind of looking at model discovery probably from a slightly more emphasis on the philosophy and the methods. So we've got a talk from Josh, then one from me, then one from Ivan. Then we'll kind of pause the talks and go into a discussion and Q&A. And I'm very happy that Blake and Doyne are able to lead that for us, but everybody is very welcome to take part. And if you have to manage the questions there, if you have questions, if you just write them into the chat or at least indicate that you've got a question there, then that will allow us to handle that, because there's so many people in the session, it's difficult to manage otherwise. And then after that, we'll go into a kind of another set of short bursts of talks. One from Twong, another from Chathika, another from Bill. These kind of have a bit more of an application theme to them, and then we'll go into yet another period of discussion. So we've kind of assigned about a quarter of the time available to discussion and Q&A, but just split it into two. And then at the end, hopefully, if we've got some time left, Chathika and Twong will introduce you to some of the tools that some of the groups have been using and developing with these methods. And then we'll just have a final reflection and close out from Josh. So that's the agenda. And I think without further ado, I will hand over, Josh, to you. So I'll stop sharing, and if you want to share your
now let's see.
Your talk slides.
Clicking on them does not do it. Can you guys see that? No. I'm not seeing a share option, Robin.
Should be down at the bottom. There should be a
there we go. Now we got it.
Option, yeah.
Okay.
And if people mute during the talks, that'd be helpful. Thank you.
Now can you see that?
We can.
Beautiful. All right. Yes, this talk is called Inverse Generative Social Science. And again, welcome to all the participants. We have a great group of real leaders in this field. And to set up the discussions and other presentations, I prepared an overview, a hopefully provocative talk on generative and inverse generative social science, including some challenges and opportunities that we can all discuss at the end. I don't want to eat into others' time, so I'll move quickly. If I'm unclear, please ask, but if it's clear and stupid, wait till the end, okay? All right, so inverse generative social science. I like the acronym iGSS, inverse generative social science, because it's the inverse problem of agent-based modeling, but it's pursuant to a generative explanatory standard that I'll talk about and applied to social science. So iGSS. But others working along the same lines use different words: evolutionary model discovery, Chathika and Ivan will talk about that, rule induction, Bill Rand, computational abduction, my colleagues at Virginia, Madhav Maratha and others, inductive game theory, Simon Dedeo and Jessica Flack and David Krakauer. I think we're all getting at similar things. To frame the inverse idea, at least as I've been thinking about it, let's review the forward, plain vanilla, generative explanation idea. What's regular old generative social science in the first place? At least as I and many others have published on it. So it's an explanatory epistemology. I want the social sciences to adopt a generative explanatory standard. And I distinguish sharply between explaining and predicting. I mean, why are there earthquakes and tsunamis? Plate tectonics explains, but we can't predict those. Why are there new viruses? Evolution explains, but we can't predict even next year's flu strain. Okay, so explain does not imply predict. It tries to identify a mechanism. Conversely, predict does not imply explain. Here are the famous Canadian lynx pelt data from the Hudson Bay Company over about 100 years. Can I predict the pelt yield on year T+1 from the previous year? Sure. Here's a beautiful model published by Priestley that does just that. It says I can have an autoregressive moving average model, and with these coefficients, I can predict T+1 from T. But does it explain it? Does it give a mechanism for the Lynx cycles? Is there anything missing? Yeah, rabbits. The prey are missing. It's actually a predator-prey cycle. So it predicts, but it doesn't really explain. So I'm saying predict and explain are logically independent. And I'm interested in a particular kind of explanation in the social sciences that I call generative explanation. To explain a social pattern, you have to show how it could emerge on time scales of interest to humans in a population of cognitively plausible agents. Earlier, I wrote that, you know, I could have chosen effectively computable or constructivist, etc. Generative was inspired by Chomsky, but by whatever name, this is the idea. And it's different than physics. It's different than equilibrium game theory and economics. It's different than optimal control theory, where agents have superhuman optimization powers. And it's different than aggregate regression, which is really a kind of macro to macro technique that might be predictive, but not explanatory. So we're looking for a bottom-up approach. And, you know, I had a simple motto for this idea, which is if you didn't grow it, you didn't explain it. The problem with catchy mottos like that are that people ignore or forget the careful and complete elaborations they condense. So the complete statement in English I just showed. But, you know, I've tried to be very clear about this. For any X, if you didn't grow X, then you didn't explain it, but not the converse. It's not, I'm not saying any old way of growing it is explanatory. It's a necessary but not sufficient condition for explanation. And this has been articulated quite a few times. And what really brings us here is that, yeah, if you didn't grow it, you didn't explain it, but there might be lots of ways to grow it. So I'm not claiming that if you grew it, you explained it, and that generative explanatory candidate is unique. There might be many, and that's why we're here, to enlist AI approaches, machine learning, evolutionary programming in the discovery or construction of multiple generators. Again, since this came up in an earlier conference with Blake and others in Virginia, you know, typically it's framed as micro to macro, grow the macroscopic structure from the micro world. But it also isn't saying that every single actor in your model has to be generated from the bottom up. So, you know, you could have intermediate actors like the Federal Reserve or the Supreme Court or other things. And to the extent that those are stipulated, not generated, then they're just not explained in the model. That's fine. A lot of models exclude, you know, not everything has to be endogenous in your model. On the other hand, to the extent that their outputs, like the prime interest rate or vaccine approvals, are generated by the internal agent interactions, then those outputs are generated in an agent-based model of the intermediate form. And that's fine, right? So it's not unique, but a really important confusion is this one that concerns the Turing test. And I say that for our purposes, the Turing test is completely irrelevant. Suppose we claim to have a cognitively plausible micro mechanism, little m, that generates a target macro pattern or meso pattern, big M. So sometimes we're told, I've been told, it's already been done. John Smith already proved that for any macro pattern M, there's a Markov transition matrix whose absorbing state is M. So what? How does the transition matrix illuminate the social mechanism that generates the macro pattern? You know, I could say behind the screen is a soprano and a perfect recording of that soprano. No human can tell them apart. But the recording tells me nothing about how humans vocalize. By what mechanism do humans generate sounds? It's wind flow across vocal cords, and the Turing test is irrelevant to that mechanism. it's as misguided as saying, to understand how the steam engine works, let's start by sampling clouds of steam. Let's collect big steam data. I can find some model that generates that same steam data, but it'll not illuminate how the steam engine works. It might even let me predict steam on Tuesday from steam on Monday, but it doesn't teach me anything about how steam engines work. Same with big word data, feed it in there and get a talking phone. It doesn't illuminate how infants acquire an infinite generative grammar long before they even have any words or a respectable lexicon of any sort. So the point is, emulation of output does not illuminate mechanism. And this has been a problem with most artificial intelligence work in our orbit. You know, yes, artificial intelligence is displacing humans in work, it's augmenting humans, it's defeating humans, but it's not yet explaining them. And this is what we want to do. We want to use these techniques, not simply to beat humans at chess, but to explain how humans play chess, for example. So AlphaZero kills everybody at chess, but it doesn't illuminate how humans play. So Kasparov beat IBM's Deep Blue computer with a completely alarming queen sacrifice. And after the game, he was asked, how the heck did you come up with that? And his answer was, it smelled right. So I think we do a lot of things by smell without the explicit calculation of costs and benefits assumed in the dominant theory of rational choice. And we want to develop cognitively plausible agents that will generate the patterns we care about, patterns of violence or economics or health behavior or migration or what have you. And there is a next generation of what I might call ortho-rational agents that include emotions like fear, social influence, conformity effects, and a whole host of well-documented errors in our appraisals of information and risk, what Simon called bounded rationality. I think these agents promise to give us a much deeper explanation of collective dynamics in all sorts of fields, economics, conflict, etc. But they, maybe my own Agent Zero, are particular handcrafted solutions of the forward problem. We want to use AI to evolve larger families of generators, beginning not with the agents, but with the target. Cognitively plausible agents, or families, or neighborhoods of them, then become outputs of AI-enabled inverse generative social science. And I think that will stand agent-based modeling on its head. We'd like to move from forward, specify the agents and generate the target, to backward, specify the target and generate the agents. And this would position us to address several challenges that are frequently lodged. So, you know, we might present a model of the Anasazi or some other thing, and someone would say, okay, fine, you found one generator, aren't there others? Well, if iGSS enables us to construct families of generators, we could say, yeah, there are others. All the following agent architectures generate the target. So take your pick or give us one of your own. It would also address this charge, I think, pretty illegitimate charge that agent models are ad hoc. You know, classical agents are not entirely ad hoc. There's certainly no more ad hoc than the rational actor, especially now that economists can choose from a huge menagerie of utility functions. I mean, max U, maximize utility, maximize expected utility, that's not a unified theory. If you can choose from an infinitude of utility functions. I mean, Blake might want to say something about this. But in any event, the inverse generators, right, the inverse solutions constitute the pre-image of the target under iteration in the computer. So what can we say about that set? This is the set where all the candidate explanations, the generators, lie. Can it be metrized, for example? I think these are basic challenges of the approach. So again, you get an answer like, okay, you dreamed these rules up and they seem to work, but what if we change them a little? Is the result robust? You'd like to answer, yeah, the result is robust over an entire neighborhood of rules, of agents, of designs. Well, what does that phrase mean, neighborhood of rules? Can we devise a metric structure over microspecifications, the agent models themselves, so that you could say that the fit is not just stable to parameters, but is stable to changes in rules, in form? We're asking, is there an analog of structural stability for agent-based models? I think that's a deep, hard question. We'd certainly like one, right? I mean, just as a quick overview, the idea here is in dynamical systems, you can put a metric structure on fields in their own right, functions in their own right. You can put a metric on, one function is ax plus b, another is x squared minus sine x. You can impose a metric structure on the infinite dimensional space of functions and can say that within a neighborhood of those, all the flows are topologically equivalent. They're continuous rubber deformations of one another. They all have the same equilibrium structure and so forth. So when you're asked, you can answer, yep, we get the same qualitative result under any small change in the functional form. All the functions in the neighborhood, a metric property, have homeomorphic phase portraits, a topological property, which is a very beautiful connection. Regarding agents, I understand a small change in numerical parameters, but what's a small change in rules in the agent model itself? Do we have an answer? We actually have too many answers. Every program can be represented as a finite string of zeros and ones. So obviously the distance between two programs, since they're binary strings, could just be the Hamming distance between those. And this has been used to evolve cellular automata with specified properties and so on. It's a perfectly kosher metric, but it may not be at all illuminating, right? I mean, it may not accord with our sense of proximity or similarity. So I could encode call mom and write a poem and eat a potato as strings of zeros and ones. And I could compute the Hamming distance between the rule call mom and the rule write a poem. Is that distance smaller than the Hamming distance between call mom and eat a potato? Which is closer to call mom? What the heck does that even mean? I changed the rule a little and the results stood up. So I think it's tricky to use the Hamming distance on this. We may not end up worrying about it, but again, I think it would repay our effort to be as rigorous as we can about this set. You can metrize a set without being able to order it, for example. That's true of the Euclidean spaces, at least high dimensional Euclidean spaces. You can also order a set without metrizing it by alphabetizing it, lexicographic ordering. You could do both, like the real numbers with an absolute difference matrix, or you could do neither and simply encode the thing as a searchable set of alternative microgenerators. And that would allow one to come up with lots of alternatives, but wouldn't allow you to say there's small variations on one another. All right. In any event, I think that would be a very fundamental step. And we have excellent examples from the group today of this type of many generator solutions. One is Yvonne and Chadika's wonderful inverse Anasazi model that came up with a better solution than the one that Rob and I and our Santa Fe crowd published years ago. So that's wonderful to see. Chadika also has inverse shelling models. Tuong Vu, Robin and I have been using evolutionary programming to understand drinking behavior. And Bill Rand has yet other solutions that we'll undoubtedly hear about. So some people argued that this would be the end of theory, using machines to develop generators and agents. I don't think so. I think we're still going to build handcrafted agents, but this additional approach changes the locus of theory from the completed agent to agent constituents, rules, modules, and building blocks. The building blocks still have to be germane to the problem. You can't say, pick a preferable shelling site and also eat a cookie. That'll generate the same segregation pattern, but it introduces some superfluous nonsense. So you have to meet defensible notions of cognitive plausibility. And again, I proffer agent zero as one of these, but we should evolve many other variants. And in some of my publications, I've said we could build construction kits of agents And we could try to grow Agent Zero or try to grow other things. And I'll talk about that tomorrow in my keynote, where I talk about building Addict Zero and other sorts of agents. All of this will still require art and human judgment, but at a different level. The level of agent primitives, concatenations, modules. The machine may give us a bunch, but we may rule some out on those grounds. Maybe the machine can't find any, and your handcrafted agent just nailed it, and you're done. There are many, all equally good. Then you have to do more work, design experiments or collect data that would adjudicate between the competing models, just as in any other science. And there might be no good ones. Of course, again, raises this question: what is a good one? Do you mean merely accurate, as in a black box machine learning type thing? But do you also require that these be comprehensible to humans? And I think the whole idea of how do you encode comprehensibility constraints into all of this is very important. There clearly are going to be trade-offs between deeply accurate trees that offer no theoretical insight and less accurate but more understandable solutions. And again, Tuong may talk about this further, but our work produces this complexity accuracy trade-off curve. So from our project on drinking behavior, here's the sort of results you get. This is in a paper we published in Gecko toward inverse generative social science using multi-objective genetic programming. And the primitives are agents can pay attention only to payoff. They can pay attention to the actual statistical patterns of drinking. They can also pay attention to norms of drinking behavior. And they also can be autonomous. They cannot care at all about those rules. And these are in effect, the agents, these John Koza-like structures are the agents. And, genetic programming solution 1 produces very low error, but it's a huge, complicated expression, this agent. This one is a very simple expression, but it doesn't do particularly well. And if you take as the fitness of these expressions some measure of proximity of the model output to the observed data on drinking, this is one such that we use, you get this nice curve that describes, or at least, it suggests this trade-off between complexity and comprehensibility and so forth. And I think that's a very important thing for the field to be thinking about. Likewise, the unconstrained machine may generate trees with more nodes than there are data points, in which case you have the sort of Borges map problem. But I think in general, are there calibration challenges that will be unique to inverse generative social science? I think that's worth a lot of discussion. All right, so wrapping up, forward generative social science. We distinguish between explain and predict, and we're interested in generative explanation that's distinct from many other types of work in economics and statistics. It's not necessarily equilibrium, it's not regression, it's not physics. Growing things is necessary but not sufficient. And we want agents to be cognitively plausible. We want more formal alternatives to the rational actor, not just gripes and anomalies from psychologists. That doesn't change practice. You got to give people a formal alternative. The generators are candidates. They're not necessarily unique. There may be many ways to grow the explanandum, the macro structure or mesostructure or social pattern that you're interested in. Backward iGSS says, okay, there may be many ways. Can we make the search for multiple generators more thorough using AI, evolutionary programming, machine learning to construct or discover families of generators, satisfying the explanatory standard with all of its desiderata. So iGSS, again, connects to that standard and the social science desiderata. That's why I like this acronym. It's not merely, can you technically invert code? And a unified social science that does both, that builds the forward and backward models and retains that standard, I think wouldn't end theory. It would revolutionize the theory construction kit. And I see this as a major initiative for our community. And I welcome the other speakers and further discussion. Thank you very much.
Thank you, Josh. If you have questions, I encourage you to write them in the chat as we go along, and we'll have the kind of discussion touch point later, but we'll save questions from Josh's talk till that point, if that's okay with people. So if there's burning things in your head, I suggest you put them in the chat, and we'll review that when it comes to the discussion time before we have the kind of the full Q&A. So, and thank you, Josh, for pretty much keeping to time. So we'll go on to the next part of the workshop, which is going to be me. So I'll share my screen with you, and hopefully you're able to see that. Great stuff. So I'm going to give you my own kind of personal perspective on model discovery, which comes from my work in policy appraisal and building models that are suitable for appraising policies that have yet to be implemented, and kind of explain why thinking about a plurality of model structures might be important in that work. And then I'll take you through the approach that we've developed on our project Cascade to work with multiple structures, the kind of framework we've built that allows us to do that efficiently, and then kind of my perspective on what the open questions are. And there's a couple of kind of voices from the past that I've put onto this overview side. The first is from Openshaw, writing in an editorial in the journal Environment and Planning A, Economy and Space, back in 1983, where he kind of looks forward to this this new future, from data crunching to model crunching, the dawn of a new era. And I need to thank colleagues at Delft, Clementine Cottonau, for pointing me in the direction of that really interesting old paper. And the rejoinder to that, which came from a PhD student in his department, who wrote a letter to the journal, the following issue, with the heading "Computerized Dreams Cannot Make Positivism Creative." And this might prelude some of our discussion a bit later. I think part of a nice story from these two is that I think they actually joined up and worked on things together afterwards. So it's a great kind of story from the past on inverse generative social science and model discovery. And I'd encourage you to take a look at those two really short editorial and letters. So in terms of my perspective, coming from this as a policy modeler, so I found it quite useful to think about things from a realist perspective. So I think about reality, and that there's entities and mechanisms that might be operating within a defined spatiotemporal setting that produce the concrete events that happen in the world. And we've got the potential to observe some of those concrete events. So this is kind of the view of reality that I'm working with as a policy modeler. How does that relate to the models that I build? Well, I'm kind of down in this gold box down in the bottom right, mechanism-based explanation. So our theories and our models of the real. Okay, what is it that's producing phenomena in the world? And the reason why I'm particularly interested in explanation is that I want to help support policy design. So I want policymakers to kind of understand how their interventions and policies interact with what we understand about the world, because these are prospective policies. They've yet to be implemented. So we need some kind of logic model or causal process that kind of explains how that policy is going to work. And once that policy design becomes implemented, then it really does become part of the real. It will link to those mechanisms and may work or may not work. But that's really where it becomes the real. But of course, both the models themselves and the design are also part of the real. And in some of our work on alcohol policy, it's been interesting to see just how a model as an object can, in fact, become part of the policy process and change what happens actually in the world. So this is just kind of my perspective on that. But there's some perennial problems with this kind of explanatory modeling. One that, of course, we you know, as good scientists, we would never do is to accept explanations. I mean, we perhaps wouldn't do it explicitly, but if we're working with one model, then maybe there's a risk that we would do it implicitly. And I've given one particular quote here of such a case, alleged case actually. So this is David Byrne, the British sociologist, criticizing Peter Hedstrom's model of unemployment in Stockholm. And David Byrne writes, the model is capable of reproducing a pattern of data, but reproduction is not explanation. We're in the territory of the fallacy of affirming the consequent. Now, this was a little bit of an unfair criticism because Peter Hedstrom says it's an explanation. He doesn't actually say it's the explanation. And this goes back to what Josh was saying in his previous talk. So, of course, he wasn't saying it was a sufficient condition to accept the explanation, just that it was a candidate. But here we see ways in which it can be misinterpreted. And there's no doubt that Byrne had other criticisms beside that one of the model in that case and the quality of the explanation. But we've also got problems with rejecting explanations, and this is a really nice study. This is a JAS study looking at 3 different candidate implementations of the theory of planned behavior in a particular study. And what these authors found is that the way such intangible notions as social norms, attitudes, perceived control and alike are implemented in a model influence results both qualitatively and quantitatively. Now, this could can cause us a bit of an issue, really. So if we've got alternative implementations of theory of planned behavior, some of which work, some of which don't, that makes it a little bit more difficult to kind of reject or not theory of planned behavior as an explanation in that case. So it's quite interesting to think about how particular implementations of models might affect how we go about rejecting explanations. So what can we do about this? So that what I'm going to kind of try and persuade you is that really we want to develop methods that are able to, on the one hand, validate a plethora really of meaningful explanations, and then secondly, to admit a plurality of those explanations within, in my case, the policy appraisal process, so that we're not just working with one model to support policy, we're working with a spectrum, and not only of model parameterizations, but of model structures of different explanations. So I'll just show you now the kind of stuff we've been up to on the Cascade project. So to start off here, here's a bit of Lego. So imagine that Charlotte P, we've got 2 Charlottes on our project, Charlotte P and Charlotte B. So in this case, Charlotte P has redescribed alcohol use in the USA within the period 1980 to 2020. Okay, so we've got some empirical evidence about what was going on in terms of alcohol use patterns in the USA. And Charlotte's going to redescribe that as a case of social norm theory, and Josh showed you a little bit of this model earlier, and Tuong will show you a little bit later. And that's embedded in a single individual level model. So what happens then is that Tuong, our analyst, extracts the building blocks of that ABM, that social norm model. So just turns it literally into components, into building blocks of Lego. And then what happens next is that our computer, which is called Disco Machine because it's got a lot of lights, uses those building blocks to come up with many different redescriptions of alcohol use as a case of social norm theory. So different realizations of social norm theory. And that's one case. So here's another case. So another one of our model builders, how he decides to redescribe alcohol use as a case of social role theory, a different theory. And then Alex, another modeler, is redescribing alcohol use as a case of social contagion theory. Okay, so that's good. So we've got 2 more ABMs. What Tuong does now is that he decomposes those ABMs again, extracts them into their building blocks, gives them to the machine, and the Disco Machine again goes away and starts using both of these sets of models, the components from these models, to redescribe alcohol use as some kind of integrated or hybrid role contagion theory. So this is pretty much what we've been up to. And the key here is that we haven't done that kind of in an ad hoc way. So to enable us to do this quite effectively, we tried to describe all of these different theories using a single unified meta theory that would allow us to quickly do this extraction into building blocks and put things back together again, using a library of theory components. So we've generated from all of these models this library of theory components, and we've done it in a way that's reasonably unified, and I'll show you a little bit of that unification in a moment. Then what we do is we put it into a system identification process that's reasonably similar to what you would use in a parameter calibration. So we've got some prior beliefs about the inputs of models and about the parameters of models, but this time we've also got some prior beliefs about the components of the model itself. And we put all that together into an ABM, a mechanism-based simulation model. And then we look at the outputs of that. So we look at goodness of fit, we look at the complexity in terms of how many terms are in that model, and we also look at meaning. And meaning is the most tricky thing, really. The way that we look at meaning is we kind of lobotomize the agents that we've got, we take them to domain experts, and we ask them, what do you think about this? Does it still represent theory? And the domain expert provides some indication of that. And using those three different measures, that kind of multi-objective approach, we iterate round and we keep going. So we change our models, we change our input and parameters, and we try to iterate towards a situation where we're getting some meaningful models that offer reasonably good fit to empirical data, and offer some kind of balance in terms of the complexity of those model structures. And then we use that as our kind of candidate set of models to take forward for policy appraisal. So the common approach that we've used, so rather than it all being kind of different bits of models built in different bits of software using different types of design, we try to unify all of that. And we use something that we call the general micro-macro scheme. We published this in JAS recently. If you look at a lot of the meta theories that exist in sociology, so Peter Hedstrom's analytical sociology, which was an elaboration of the Coleman boat, but also others that kind of claim to be different, like Margaret Archer's morphogenesis, Tilley's three mechanism model, even perhaps Rob Stone's elaboration of structuration, although I might be pushing things too far there. All of these kind of have some similarities in that they consist of a macro level with things such as institutions and norms and networks in the case of an ABM, or relations, and a micro level, which could be individuals, but in some cases perhaps just represents agency rather than individuals specifically. And then different types of mechanisms that relate these two levels together. So I'm using the language of Hedstrom here. So we have situational mechanisms that say how those microagent states are influenced by their exposure to macro entities, either through a macro entity itself or through situated micro-micro interaction. Then we have action mechanisms that explain how behaviors are influenced by the states of those microagents. And then we have transformational mechanisms that show how the collective behaviors of agents come together to change macro structures, including relations. So this thing, depending on how you look at it, can be criticized as methodologically individualist, but it doesn't have to be. It really depends which of those different flavors you choose to take. And we found it quite useful because all of the different theories that we've looked at in our work, we've actually been able to map them to elements of this structure. Because we're using a common kind of conceptual framework here, that allows us to build a common software architecture, which Twong put together, which is an abstract software architecture. It's object oriented and it uses something called the mediator design pattern to allow us to integrate different theories together. And there's structures and there's micro agents within that. I won't dwell on that in any detail, just to say that there's this software architecture. And once we've got a software architecture, we can go on and actually build some concrete ABMs. We also do some quite fine-grained model discovery. So we extract grammars, so recipes for building agent-based models from the heart of our ABMs. And we use a genetic programming approach, so an evolutionary algorithm, to conduct the search over that space of models. And we are typically working with three different measures of fitness: empirical fitness to targets, complexity, and degree of meaningfulness. And then I'll end just with kind of my take on the open questions. So, one that we've found the most challenging over the last few years is kind of encoding meaningfulness in that model search process and being able to identify when a model structure is meaningful in terms of theory. Certainly not everything that we produce is meaningful, at least as our domain experts perceive it. It would also be quite nice to move towards a fully probabilistic framework. So obviously there's a lot of interest in approximate Bayesian computation approaches that would allow us to kind of resolve posteriors for model parameters. Kind of needs us to think about priors for model structures and kind of building blocks of model structures in a consistent way, and I'm not sure we're really doing that yet if we want to go to a fully probabilistic framework. And then finally, there's the computational complexity of this process, because it's a bi-level problem. On the one hand, we're searching for structures, and then within a given structure, ideally, we want to search across that parameter space as well. And that's quite computationally challenging. So could we use surrogate modeling to help us with some of that? And that takes us back to Josh's question about metrics for distance between model structures, because if you want to fit a surrogate model, you want something that's reasonably well behaved in the space of model similarity, structural similarity. Yeah, and the papers, these are all open access if you want to look at them. We've got the Jazz paper, a paper in complexity, and the Gecko paper that Josh mentioned as well. And please do contact me with any questions outside of this discovery workshop itself. And finally, I just want to thank the funders, NIH in the US, and all of the big project team we have on Cascade. So thank you very much. I say if you have questions, please just add them to the chat as we're going along. We'll do one more talk from Ivan, and then we'll go into that discussion and Q&A. Okay, thank you very much. So Ivan, over to you.
Thank you, Robin. Let me share my screen. Great, my name is Ivan Garibay, and I want to start by thanking Robin and Josh to invite me to co-organize this, and thanking you all to be here. So my talk is titled From Deep Agents to Inverse Generative Social Science. So I want to take you quickly a little bit on the background of what we've been doing. This is, you know, in a high level, it's a project funded by DARPA. We've been working on this for 3 years. We have 1 more year to go, and it's trying to develop simulations of online social media behavior. So that's the context of what we've been working these years. And also, you know, in this talk, I'm going to give you an overall view very briefly. We have 2 more talks by Chatika Gunaratne, who is going to provide a little bit more detail on one particular implementation of these ideas for social media, as well as the overview of the tools that we have developed, and they're available on GitHub. So thank you to all the collaborators in this project. Bill Rand is going to give a talk later, is a copy of the effort, as well as Josh briefly helped us as a consultant. So thank you, everybody. And the idea here originally was to expand on Josh's Agent Zero with machine learning and artificial intelligence and some automatic rule discovery. So our project is called Deep Agent, and we see it as following the tradition of generative social sciences. So that's how we approach this modeling of social media. And in loosely speaking, is taking, as I mentioned, Agent Zero ideas of social, emotional, rational components of theory driven building of agent-based models, but is adding as needed AI, big data, and things along those lines. And basically the goal of doing that is to go from few handcrafted rules to larger rule sets that can be discovered and managed in a semi-automatic way, and potentially help us tackle real world problems like the ones we have on social media dynamics. So in this project, we have published in multiple areas, including information diffusion, frameworks, many of the social phenomena that we see now, like narrative, disinformation campaigns, polarization, influence, etc. But what I'm going to focus today is on something that we call evolutionary model discovery. So inverse generative social science, just echoing what Josh set up in his in the first talk of the workshop. The way I see it is in game theory, we look at the rules, the basic rules of interaction, And game theory is focused on calculating the outcome of that game. Opposite to that, or in some way inversely to that, we have mechanism design theory, which look at, given a desired outcome of a game, what are the rules that will enable that outcome? In an analogous way, we can say GSS, or generative social science, goes from micro behavioral rules and generate observable macro phenomena. Like George was saying, if you didn't grow it, you didn't explain it. So that's kind of the core of the method. And we want, or we are looking at it in the opposite way, which is given an observable phenomena, what are the micro rules of micro behaviors that could generate them? And in that simple kind of change of focus, I think opens a lot of questions, like are the generator rules unique? Do we have a large population of generators? What are the characteristics of that population if we find them? Do they have something in common? And could that tell me something more than about the real world just matching, right? The observed microphenomena. So our interest in this particular part of our project was to develop iGSS methodology to correctly identify and characterize the causes of emergent behavior in social processes and systems. So that's kind of our goal for what we're looking at here. And for that goal, we tried different ideas, and we're going to focus on one just for time here, something that we call weak causal inference. So if you look at the real world, we can say we observe microphenomena, and there must be some micro level behavioral decision-making phenomena going on that after some interaction produce this observable macro phenomena. If we assume that, and we accept that assumption about the real world, then when we try to model something using generative social science, what we're looking is theories, micro behaviors that we can ascribe to agents, have them generate a macro observable phenomena, and we try to match the real world microphenomena with our generated macrophenomena in a simulation of the model. And the question here is, what exactly have we learned at the micro level if we do match the observable phenomena? And well, you know, we have shown one instance of one set of rules that generate the observable phenomena. Somebody, of course, can argue that there may be many, many instances of those rules. So if the essence, what have we learned is very little about the micro rules on the real world. And that's something that we think it could be improved. So we want to discover stronger causal relationships. And how we do that? Well, number one, as Josh was saying, is, well, we go from one set of generators to many. One way of doing that computationally, simply we just put a machine learning algorithm and start generating many, many set of rules that actually match real world phenomena. There are many technical issues here. I think the most conceptual issue is what Rob calls, or Robin calls, the building blocks, right? So how these building blocks are meaningful, how they are meaningfully recombined, how do we have them all? So the way we approach it is we base these building blocks from social theory, that compose of social theories for the phenomena we're observing, or that we think are important for that phenomena, into causal factors. And then we mix and match those causal factors using ML and different technologies. And then we generate a large set of potential generators. Once we have that set of generators, the next thing we can do is we can analyze that set of generators. So we can ask questions like, are these generators homogeneous? So if they're homogeneous, they tell me far more than just having one. If we have explored extensively many social theories and we have a homogeneous set of generators, that basically implies to me that I have a stronger case to make about what is going on in the real world micro behavioral rules. Are they heterogeneous? Do they have commonalities? Do we have common causal factors that are present in every set of these generators, population of generators? If so, then probably that causal factor is, again, something that could be, we can claim more strongly that it could be present in the real world micro generator. So we go from, hopefully, if we did a good job in exploring a vast amount of causal factors, to telling me something about the nature of the people and their decision-making processes that are involved in this, in generating these observable macro phenomena. So one, of course, we have to start somewhere. Those are broad ideas. So we first attempt to implement some of these and getting some results we call evolutionary model discovery, and you can see there the link of the GitHub repository for this. So in the first part, as I mentioned, generating not one, but many models, right? The way that we made that tractable at this point is we just focus on one rule. So when we have one model, we target one rule at a time, one behavioral rule at a time. And then we create a representation space of factors, as I mentioned, and we have a couple of methods. So to do that in a systematic way, and then we represent them in a GP3. And of course, we don't only look at social theories for the subcomponents or for the factors, we also look at data. So we have a combination of both to create this exploration of a space of rules. And the second part of this, as I mentioned, is analyzing this. And there are many things that we could analyze. So we just selected one first thing to analyze that we call factor importance. And this is related in the machine learning community of what we do for feature importance. So we basically reuse some of their methods, use a simpler random forest regressor analysis that correlate factor presence on the set of generators with the fitness of that generator in the model when it runs on the model and calculate the observable phenomena closeness to the real world observed phenomena. And we do feature importance analysis. So that's a very simple way to move into analyzing that population of generators. So just by doing that, we have tried several cases. This is one of them. As Josh mentioned, this is the original work by him and Axtel on the Anasazi. And we focus on one aspect of that problem, which is the farm selection, which in the original model, it was simply move to the next closest location. Introducing new causal factors and new theories in the mix, and then doing this regressor analysis to find the importance of these causal factors on the entire population of potential generators, we found that there are other factors that actually are salient for this farm selection mechanism, and they are higher soil quality. So basically, potentially what we're saying is, if this all makes sense and is done adequately, we could claim that the Anasazi thinking was, I'm thinking in higher soil quality first, then I'm thinking in higher social presence next, and then I'm thinking on going further away from areas where farm plots failed previously. So that was the rationale that they used to select the next farm or to move and relocate when their current farm was exhausted. So I know it's a big claim, but we're moving towards trying to provide more insights on actually what are the rules that are in play in real human decision makers. So we did the same for the segregation, the Schelling segregation model. And as you know, there is mixed patterns are the state of the art now, Hadnat-Benson model. And we explore many causal relationships from different theories to figure it out which one generate the best mixed patterns that we observe in real world. And turns out that the causal factors that come on top are resistant to moving from their current location, preference for less crowded neighborhoods, and third is the original Schelling formulation of preference for higher radius similarity. And more interesting than this, none of these factors alone is able to produce a high score. So we can see the trend on how you need to mix these factors in certain order for them to be effective as generators. Okay, that's 100 miles per hour or kilometers per hour description of what we have done.
Thank you, Ivan. Great stuff. So that moves us into the first of our discussion and Q&A periods. I think we'll start with inviting Ivan and Doyne to kind of lead us off with some thoughts, and then kind of take things from there.
And remind me how many minutes
Blake,
do you want?
Blake and Doyne, yeah.
Probably 5 minutes maximum, if you can contain yourself to that.
I see we're moving pretty late on the schedule.
Yeah.
I've got my schedule up, so let me try to compact to like 2 minutes maybe. I'm going to go for that because I want to hear. I mean, I know also the chat is going there too. So thanks very much to the whole crew of you for presenting all of these ideas. I'm going to sort of, and it's been very nice to be here. I'm not in Italy, of course, right now, but the idea of going backwards and pulling agent, going backwards and developing a reasonable set of agents is I think a very interesting and powerful one. I think in many instances we are going to want to know, in some more than just our casual frameworks of us just trying casually along doing stuff to see what matters, what behavior is coming, what behaviors are coming from different types of micro agents. I have a couple thoughts on it. One, I think it may have been Josh, but all of you were sort of blowing off sort of big data a little bit. I'm more optimistic, and I think Bill may speak to that later too, that the sort of rule inductive approach still has some value to it, that if possible big data we can nail down pretty tightly, hopefully in some situations, with these kind of newly available data sets. So I'm still open to that, and that changes the problem around a little bit because it makes it easier because you have more constraints on it. The second thing I'd say is it's also, remember that there's a lot of other tests on these agents, and particularly things I've looked at a lot are sort of really, I've spent, I think, my life doing really internal model consistency, or the original goals of much of the work in adaptive and evolving agents was to understand which behaviors would hang around, which would leave. You were essentially putting everything under evolutionary control, was what we used to say. I mean, I've even written some recent papers just demonstrating that allowing just local adaptation in certain models that people think are really successful. These are some of the finance models that have sort of run the world, right? Not in the agent-based world. They actually have micro inconsistencies in them that allowing some small amounts of learning. You remember that these agents are unstable relative to that. So there's a bunch of very important consistency checks we can still do thinking about adaptation and evolution. I think the other big problem that sort of hits my head on this is when I think about inverse generative stuff and trying to generate the types of evolving, you've already got it, if the models that I think about where there's a lot of adaptation and evolution going on in the model, it's essentially doing inverse generative stuff on the fly while the model is running, trying to think about how to feed back this problem, which I'm sure other people will say is clearly pretty hard, but I'm impressed with how you guys are trying to do it. It will get even harder at that framework. And then the last thing, which is on a different tack entirely, is a reminder that in many agent-based worlds, it's really, the environment is really, and the structure around the environment is often what's under study. And, the agents, we hope that the agents are almost a second order story. I'd say things like, and maybe Doyne will come, market microstructure, where a lot of our features are extremely robust. And we hope they're not really, we often use what are kind of near zero intelligence agents in these platforms. And it's the environment that's really the kind of, or institutional structures, which are the part that's under study. But I did say, I promised to keep myself very quick, so I'll wrap up there. If I have more to say, I know I get to come back like an hour later.
Thank you, Blake. And Doyne, do you want to have a couple of minutes?
Sure. It's difficult to summarize such a profound topic in a couple of minutes. Let me just focus a bit on Josh's talk. I basically agree with everything you said, Josh, but I think there's a lot of devils in the details and a lot of nuance, and so one has to be very careful. And maybe I'll begin by saying this debate about prediction versus explanation is one of the oldest debates in science. As you may know, there was a major debate between the Cartesians and Newton concerning action at a distance. The Cartesians said action at a distance is not an explanation of gravity. You have not explained the phenomenon. And they're right. We still haven't explained the phenomenon of gravity. You know, we're still seeking models that actually tell us how the interactions work. It's the frontier of physics, and it's stuck. It's been stuck for a long time. But, you know, in the end, Newton won that because people realized those models are really useful. Celestial mechanics, we predict, and it's not a generative model, but it is a causal model, and that's different than a machine learning style or statistical model. So I think it's important to parse causal model versus generative model, because you can have very, very useful causal models, even if you don't know how they're generated. In the link series that Josh showed us, okay, instead of doing the AR model that Priestley used, you can use a predator-prey model a la Volterra. And that is a more causal model. It's not a generative model. And I think often if we have good causal models, we're on a good path. And now, of course, a generative and causal and predictive model is what we really want. But that's like, you know, hitting a jackpot we almost never can hope to achieve. I think we really should ask, is the model useful? And another thing I want to stress is I think knowing that we have we can have a causal model that looks nice and sounds nice. That was the case with Descartes. You go back and read Descartes' model of gravity, everybody loved it in its day. But, you know, it bears no relationship in the end to explaining anything empirical. But it sounds really good. Ultimately, you have to have a model that both has compelling reasons for its assumptions to exist, but that also is useful for making predictions. So you can't really separate those two problems at the end of the day. I think it's important to really keep one's eye firmly on parsimony. I'm a follower of Rissanen. Jorma Rissanen, if you haven't read his stuff, he basically says the best model is the one that explains the data with the minimum number of bits, and the description has to include the number of bits it takes to describe the model. And now, this is something important to bear in mind because even in physics, we worry about these same issues. And debates are ultimately resolved. As Einstein famously said, you know, a model should be as simple as possible, but no simpler. And that's really a statement of the same principle. So now, Josh talked about structural stability. It's wonderful when structural stability exists, but there are many places in the world where structural stability doesn't exist. I wrote several papers in the old days in chaos theory, where you have the logistic map Rx1 minus X, and you can show that as you vary R, you get chaotic solutions. The question is, what's the measure of those chaotic solutions? And people were very worried about it because you could show that arbitrarily near any value of R, there was a stable periodic solution. So it is absolutely not structurally stable. Nonetheless, chaotic solutions have positive Lebesgue measure. So I was one of the people that helped show that. But so you can't count on structural stability being there. If the world is structurally stable, then yes, you do want a structurally stable model. But if it's not, forget it. It's the wrong model if it's structurally stable. But I think it all goes back to this question. I mean, at the end of the day, we're still using a lot of common sense. And I think you have to keep a firm idea on what did the model actually predict? What evidence do I have to believe the model? Frankly, in the last two presentations, I didn't see the evidence that made me say, oh, I believe that model. This may have just been the presentation, but when I hear a presentation, I want to see either this is just a model about ideas and here's some cool ideas, or I want to see here was what we was trying to explain, here's the data, this is why you should believe it. And I saw some nice ideas, but I didn't see that last proof or let's say the compelling evidence. And I think all too often in agent-based modeling, we fail to make a convincing case at the end of the day. And the convincing case is often an intuitive thing. So there's no fixed rules for how it's going to happen. Thanks.
Can I spring to Yvonne and Chatika's defense on one point?
Sure.
Which is simply that they, in the actual published paper on the Anasazi, they do show, an actual fit to the true data, and that it does better than the Rob and Josh version. So I take your point in general, of course, that you'd like to show us the, show us the data, show us where's the beef. But in their case, they just didn't happen to show it in this talk. But
yeah, no,
that's okay. No, but I mean, I think your points in general are very well taken and very interesting. So thank you.
Yes, I'm relying on Twong to defend my honor in the next session in response to that one. In terms of other things coming up from the floor, I just was reviewing the chat. I think von der Jager, that's a really interesting point around empirical a complex reality. The reality may manifest itself in an infinite number of ways. Do you want to just elaborate on that a bit or introduce it? It's not compulsory, but
I think you're muted, Vonder.
Set of earplugs. You can hear me now?
Yeah.
Yes.
Okay. That's basically my experience in some projects is that the value of agent-based models sometimes is in explaining to people that the world is more complex and unpredictable than they thought before. That's almost an inverse way of using these models, because usually scientists are expected to reduce uncertainty. And my experience is that in particular policymakers can be supported by confronting them with a very fundamental level of uncertainty. So I think, oh, there's some racing. I'm sitting outside and going in now. I think that's also one perspective that might be very valuable in using agent-based models. And if you think of backwards casting of models, I had one thought that might be interesting to see to what extent the current present situation can be explained from multiple different situations from the past. So basically, it's a kind of a multiverse perspective on reality, of course. Mm-hmm. This might be very confusing, but perhaps it is also very confusing.
Yeah, thank you, Vonder. I think one of the things that, in terms of that spectrum of realities, one thing that kind of encouraged me to really go at this topic back in about 2012 was I was working on alcohol policy modeling and a floor price known as minimum pricing for alcohol, and part of the criticism we got was, I thought was almost, nihilistic, in that it was anything can happen. This is putting in a floor price. Now, a floor price is controversial, but I wasn't sure that it was limitless in terms of the possibilities of outcomes. I mean, it wasn't going to cause gin riots in the UK. It wasn't going to cause complete abstinence in the UK. And I did feel that there were bounds on the possibilities of what might happen. And that implicitly that hopefully meant that there were some bounds on the set of causal explanations behind that. But I was always slightly dissatisfied that we kind of only had one explanation and that we were working with. So yes, multiple explanations, but perhaps not limitless. Some discussion of the Anasazi. Any more specific questions about the first set of talks?
Can I float an idea? If people, I don't want to interrupt chatters, but so this sort of to Doyne's point, I mean, I think it might be interesting. So Chatika and Yvonne have done two kinds of exercises. One is the Anasazi exercise, where the data is real data. And Chatika's is the Schelling model, where it's artificial data. And I wonder, as a proof of principle, it might be productive to think of other existing agent models, like the Schelling model or the game of life or Sugarscape or what have you, where we can produce very clean data about the output and maybe use inverse generative techniques or evolutionary model discovery to find more generators for artificial societies. That would prove the idea, and the data is in some ways cleaner, better than true data. Does that sound? I'm mainly asking Doyne whether that strikes you as a kind of reasonable way of showing, you know, that you say, show us the proof. For artificial systems, it might be pretty compelling stuff.
My graduate student, Donovan Platt, has written a paper that was recently in JD's Journal of Economic Dynamics and Control, where he takes a bunch of models ranging from fairly simple ones to more complex agent-based models and uses them to generate data. And then he asks, can he fit the model, the model, he knows the process now, can he fit the model to the data? And that's hard. Actually, even when you have the correct model that actually is the model that generated the data, backing out the parameters for that model in an ABM is a non-trivial exercise in general. He tests a whole bunch of all the proposed algorithms for doing this and finds the Bayesian algorithms are the best. And but it's a sobering exercise in that, of course, it gets much worse when you don't know the generative model. And but I think there's a huge amount to be done there. It's a case where getting to the state of the art involves really processing. I mean, you really have to get up in the cloud and use tons and tons of computer time, because as soon as the model gets non-trivial, the evaluations get really expensive. And you have to really simulate the model millions and millions of times to do this kind of fitting procedures. And we're still some ways from being able to do it fully using time series data and taking advantage of all of the linkages and also dealing with a data assimilation problem, which is, you know, one that's been solved significantly in meteorology, where you have the problem that your data that you can validate the model against is not in the same form as the data that was, as the entities that the model is couched in terms of. You know, and whether we don't get clean measurements of temperature and velocity on grid. And similarly in ABMs, you typically don't, if you're really trying to predict something, you don't have the measurements you really want to fit the model. So there's a ton of problems there to be solved. And I think it's a big and important frontier.
Thank you, Doyne. I think we'll have a second opportunity at discussion, but I think we'll move us on now into the kind of application talk. So Tuong, are you ready to kick us off?
Can you hear?
Yes, we can hear and see. Yep.
Yeah. Okay, so I wrote really quickly on cascade alcohol use modeling, and basically the purpose of this talk is show you the evolution of our model discovery work. So this is just like what Robin already covered. We have a conceptual architecture, which is called the general macro scheme. We build a software architecture, publish it in JAS. Then we build a models using a series theory, social norm theory, social role theory, contagion, and rational choice theory. And within the agent itself, we use theory of planned behavior combined with dual process for the action mechanisms when they make the decision, daily decision. And also for this kind of public health simulation, we need micro simulation, which is a synthetic population of US from 1980 to 2010s. And this is dynamic population where you have agent die over time, and then you have new agent join the models when they are being born or they are migrate from somewhere else. And then with all of these models, we perform the model discovery work. So this is the publication. So the first paper is we use genetic programming with the models of social norms. So in these social norms models, we have at the macro level, we have injunctive norm, descriptive norm. And at the micro level, the individual have a group identity, which is how they consider their drinking in groups. So like your drinking, if you are a male in 20, will be you will be considered it very different to someone male in their 60 or female in their 20. And then you perceive this is how you perceive these norms, and for your drinking behavior, it will be affected by your norms, your autonomy, and your desire to drink. So when we design the models, we have this equation that is the daily drinking disposition, like how likely the probability of you having a drink. It's a function of autonomy, payoff, and then the other way on this side is the weighted sum of the average of the injunctive norm and the descriptive norm. So in this equation, your payoff is your desire to drink. So whether this is like trade-off between whether you follow your desire or you just follow the norms of everyone. So when we're designing this model, we're thinking, okay, this is the mean. Can we use other equation for this, like geometric mean, which is the square root of the multiplication of injunctive norm and descriptive norm? And so with that further, we say, okay, let's try to do the model discovery on this equation. So the distribution will be equal to something. For that, we design a process of the model discovery. So the model will already be by the expert. And then we have to abstract a set of primitive. This case, the building block of what you want to perform the model discovery on. Then you do a parameter calibration, you evolve the structure, and then we recalibrate it to see what happens. So the evolve process, really quickly summary, is we have a population. We evaluate the model structure by comparing the simulated data with the empirical data to see which one perform better. We do a reproduction, which is like we take two structure and then we create a new offspring that related to that two structure. And then we do mutation where we slightly change the structure at the random places. And all of this we feedback and have like a new population. And then we keep going through the loop until we have somewhat good fitness in the population. So what is the building block in this work? So in this work, we had the drinking distribution. The building block, if you look at the equation, we use 4 variables. So that they are called terminal, right? So it's like autonomy here, payoff, and then injunctive and descriptive. And then we have function, how you combine these building blocks. So this is the Lego pieces, and this is how you put the Lego pieces together. So we have like all of this equation, plus, minus, multiplication, complement, and then we introduce minus as well and root, square root, to see whether we can have something interesting. So after the model discovery work, this is the Pareto front. So this is what Josh showed. I just put the actual disposition equation here so you can see. So basically this is like the trade-off surface of the complexity. So on the top it's really complex. And then when you go down, the complexity reduced. And then the trade-off with model error. So on the left-hand side, this complex model very low error, but as you go up, you go to the right-hand side, these simple models will be less accurate. Then I just want to show you the time series of the calibration. So this is after the parameter calibration. You see that the red is the empirical data, and the black is the result produced by the simulation. And this is before the model discovery work. So we do the parameter calibration. We have 3 panels. The prevalence of drinking. So how many drinker in the population, the percentage of drinker in the population. The frequency, which is the day per month that you're drinking, and the round per day, which is the quantity. And then you have male, this is the triangle, and then female is below. So you see male always drink more than female, but we have some problem trying to fit with this prevalence here when it keeps increasing, and you have this blip here. So after the model discovery, what do you get? so you get this. So the prevalence actually got much better. This is much better. So we only have a slight trouble with quantity. It's not really best fit, but this already look much better than the human models. So what is the insight from this work? First, we found out that past behavior predict future behavior. So if we have the simplest equation is your drinking is just equal to your payoff. This means that you just follow your design to drink. You just follow whatever you do in your past. The second is we need to involve normative concept for lower error. So the top is the lower error as you move from bottom to top. So you see that here, this is just using payoff, and then now you start to use descriptive norm. Now, and then you start to use autonomy, and then you start to use injunctive norm, and then you get better and better. And the last one is that the effect modifier through square root. So try to adjust the model a bit. When you look at here, just payoff to payoff, and then just square root of payoff to have a slightly better error. You can look at the paper to study this more. And now we move to another study where we use a RAMA-based approach to deal with the models called for social roles. So in this model, we're using a RAMA. We introduce a RAMA. So this process using a RAMA because it allows you to constrain the structure of your program. And it also flexible in a way that you can slightly change your RAMA and then you don't have to change much about the model discovery process. So this is an example of the RAMA where you have function x multiplied by x plus y can be generated by this RAMA. So it's like the expression can be either a variable or it can be expression operator expression. And this variable can, let's say, x, y, and z. And the operator can be plus, minus, and multiplication. So what this RAMA by agentic programming is that from this RAMA, it can build this kind of tree where you say expression is called expression operator, right? And then it keep going down, you will have this equation in the tree. So the same, we come back and we say, okay, we need to redefine our framework a bit because in here we want to involve a domain expert to study the theoretical credibility of the models. So basically, the same, we build models, but now we talk with the domain expert trying to look at the credibility of the models. And we keep doing this until we have a credible models. After that, we abstract a set of building block. We define a RAMA. We do a parameter calibration. We evolve the structure again through the same genetic algorithm process. And then now we come back to the human domain expert to see whether these models are actually theoretical credible. If it's not, we come back and do this whole loop again. And if we're satisfied with the result, we just done with this. So just quickly about the structure of the social roles model. So your agent can have certain roles. It can be married, it can be employed, it can be a parent. And this will have a role strain which affect the agent drinking. So agent can drink to cope, like you had to work and it's really stressful, so you drink. Or maybe you are a parent and you have to come back home, take care of your kids, so you cannot drink. This is the schematic of the role models, which is quite complicated, so I'm not going into detail. But basically, your drinking will be affected by the role strain, your long-term disposition to drink, which is your drinking history, and then also opportunity to drink in the home and outside the home. Generated by the roles. So this opportunity is quite important in alcohol use modeling because we want to model on-tray and off-tray, which is the case where you go out and drink in restaurant versus when you're drinking at home. So with that, we define the RAMAs. So the RAMA is quite complex, but basically this RAMA, the difference between this and the norms model is in the norms model, we only look at the disposition function. So just a tiny piece in the whole models. But in the roles model, we expose the whole models to the model discovery process. So you have all the mechanism, like some of them we can turn them on and off, and some of them just like role load, you can actually give the structure to the equation of the role load, all of this operator, and then we include a set of constants from both like we pick and then sum up from the calibration process. So what this process produce? So here you look on the right hand side, you see this is the same, the Pareto front, and then we have 14 structure on the Pareto front, and then the blue here is the reference model by the human, and you see that for the model discovery process actually find the model that perform better and also less complex than human models. And then we also really care about theoretical credibility in this study. So we set out 3 criteria for that. So the first criteria is that at least one, the structure must contain at least one of the theory construct. And then the construct must be representing mechanisms. And lastly, the equation must be compatible with the causal logic and evidence based from the theory and the literature. So after we're talking with the domain expert, we only find 3 out of 14 to be theoretical credible. So I will show you the time series of these credible models. So the ray is the target data that we calibrate to, and with the arrow band, and the pink is the human models, and then in this model we calibrate by prevalence, frequency, quantity, and also heavy drinking, but we also split it by the number of rounds. So you have no rounds, you have 1 round, 2 rounds, and 3 rounds. So it's just like round count. And you look at this, you see that the human models have some troubling dealing with the people with no rounds. You know, it cannot work for these 3, and it also struggling for frequency here as well. Yeah, but now you look at the credible models that generated by the model discovery process, which is the green one, the orange, and the purple. Okay, and actually you see that they are performed better across all of that, but they still, even the model discovery process still struggling for heavy drinking of the people that having on 3 rounds. But one of them actually performs slightly better, but drop again. So, and then we come back and say, okay, what is the insight that we can learn from all of this structure? And you have to look into the paper for more details, but basically we have to sit down, look at the structure, see, and compare that with the literature to see whether they match or not. So now we're moving on from single theory to mutable theory. So we have norms and then we have roles. And then we say, is it worth it to actually do mutable theory, or you just build single theory for your phenomenon is enough? So if you come to the tutorial on Tuesday, I already show this example. So we have a norms models with this element in the drinking decision making, and then we introduce a contagion theory into that models. So in the contagion theory, the agent will have a social network, and then they can get the average drinking from their friend. And then you can look at this average drinking as a descriptive norm. So it's like a localized norm, while this injunctive and descriptive norm up here is actually a global norm of everyone. So we want to represent the norm from the wider environment, but like also from your proximal network as well. And when we run the calibration process, you will see that the hybrid models actually have a lower error and lower variability when you compare to the single theory models. So this is a model discovery work that's still in progress. So in here we combine the norms and roles model at the drinking disposition level. So the drinking disposition is like how probability of having the nth drink, and then we categorize into a set of one, like you have first ring, you have second ring, and so on. And why we want to do this is because let's say we think of example like me. So my first ring, let's say I can just follow the norms, you know, because everyone in my friends started to drink. I want to go out for a drink, so I go with them. Second drink, suddenly the rules start to be involved more. And let's say I'm not a good drinker, and I have to work tomorrow. So I say, okay, because I'm in employment, so that's my roles. So in my second drink, I have started to think about it. And then when it comes to the third and fourth ring, I might say, you know, I have to work tomorrow, so I don't want to do that. So at the third and fourth ring, the roles actually 100% of my decision making. So this is the rammer that we come up with. It's quite simple. So you separate it by the category, and then you have row distribution and norm distribution, and then you can combine it either by weighted sum or just a square root of the multiplication of the two, and just some constant. And then we find some interesting result with this, but we're still discussing this with the domain expert. And then we move on to another study where we looking at the reference group, which is the group identity of the agent. We say not because like in the original model, we just have sex and age group. So now we say, let's say we allow them to construct and the model discovery can work with this. And then it can construct by these demographic variable, sex, age group, race, and the three role status. And the rammer, this is rammer we come up with. So we just have to adding the reference group into the rammer, and then we list on the demographic variable that we want to be included in this reference group. So this reference group can be constructed by 1, 2, or 3 demographic variable. So you see, this is the advantage of the rammer. You just have to adjusting it a bit, and then you still have to do a lot of coding to interface the rammer with the actual models, but you don't have to redesign your whole process. And finally, we from all this work, we say that our approach can find new theoretical, meaningful, and interpretable mechanisms. And the goal of this is just like assisting the human model. It's not for replacing the human modelers. Also, it's very important that you involve a human domain expert, because some model can be really complicated internal theories. And finally, we hope that we can incorporate additional theory into it. We can have a novel combination of mutable theory and push forward the knowledge discovery and also theory development based on the fusion of data-driven and theory-driven method. That's it for me. Thank you.
Thank you, Tuong. I think let's move straight on to Chatika's talk.
Sure. Thanks, Tuong, and thanks, Robin. Let me get my presentation up. Yeah, are you able to see the presentation view?
Yes, we can.
We're seeing your view, Chatika.
Yeah.
Oh, okay. Yeah. Sorry. Okay. Is that better?
Yes, that's good.
Okay, thanks. Yeah. Hi, everyone. I'm Chatik Gunaratne, and I'm from the Alpha Group at MIT CSAIL. I'm going to talk about some work that I did for my dissertation over at the Complex Adaptive Systems Lab at University of Central Florida under the supervision of Ivan, who spoke earlier. This work was sponsored by DARPA and AWS. And it's about understanding factors that affect the prioritization of responses under information overload on online social media. And we use the evolutionary model discovery approach here, which has been discussed in some of the previous talks. And the QR code on the bottom right leads you to my dissertation where there's more information. So as you've been hearing in some of the previous talks, with most agent-based modeling projects, we want to start with a bunch of theory and a set of data. So what we do is we bring this theory and data together to create what we call hypothesized individual scale generative mechanisms, as you've been hearing in the previous talks. And with an agent-based model, we then embed these mechanisms as submodels or rules within our agents. And our agents are then able to go about, act autonomously with the environment, the simulated environment, according to the rules that we've now specified. And our hope is that we get good simulation output and we then validate it back against data. Usually the validation step involves comparison against macro data, since the highly interactive nature of agent-based models allows it to produce emergent phenomena. And we can take this a step further and we calibrate parameters in order to fine-tune our agent-based model towards the macro data set that we are trying to replicate. Now, this is where most studies stop, but what I want to highlight in my talk is also what's been discussed throughout this workshop, is that the rules remain the same. The hypothesized mechanisms that we embed in our agents stays the same. Of course, if they're parameterized, they might change to some extent, but their structure, as Tuong described in the talk previous, remains the same unless we use some sort of genetic programming in order to change how factors combine and generate new rules and new mechanisms within our agents. So the evolutionary model discovery framework does exactly this. So it begins by taking your agent-based model and a set of hypothesized factors of decision-making that you have a hunch that might affect the underlying mechanism that produces the macro phenomena that you're interested in. And then it throws that into a genetic program. And the genetic program then produces generations of agent behavior rules and tries to better fit macro patterns in data according to a fitness evaluation that you provide. And it does this over a certain amount of generations. With each generation, the set of models, alternate models that are produced get better and better. So basically what you're doing is you're producing these alternate universes which have different agent brains represented within them. Now, we don't just stop there. We take this a step forward, and we understand that there's, due to the stochasticity of agent-based models, there is a lot of variance produced in our output. So we actually take the factor presence to fitness data that's produced by the genetic program, and we train a random forest regression model. And we use that random forest regressor then to do a factor importance assessment so that we're able to identify within all of the different behavior trees that are produced, what are the factors that repeat themselves that are prominent throughout the winning solutions, and how they affect the reprediction of the fitness data that was produced in this in the search space of the genetic program. So once we've identified the important factors, then we go back to the genetic program data and we try to find out what the optimal factor presence was for those important factors that we're concerned with. And the evolutionary model discovery framework is also available as a generalized Python package for use with your NetLogo models, and you can follow this QR code at the bottom left to go and grab that. And I'll talk a little bit more about it in my tools talk towards the end of the workshop. So at the core of this all, we have the idea of a causal factor. So what is a causal factor? We define a causal factor as a hypothesized unit that's human interpretable, that we guess has an important impact on the emergence of the macro phenomenon of interest. So formally, this is very easily broken down into a set of commands, information that is returned, for example, a subutility, and that could be compounded into a utility function, for example, and then some information that this factor requires, such as the state of the agent's neighbors. And in evolutionary model discovery, these factors are strongly typed so that you're able to control how they combine and produce constrained trees as well. So the resulting behavior trees will look something like this, where you have leaf nodes that represent theory components combined with operator nodes. And then they're finally evaluated by maybe a min-max or some selector that's able to select whatever set of actions that these theory component operator branch provides. And it can then compare it against a social network configuration, for example, and choose the best behavior to be performed by that agent given its environmental conditions. And so the reason we use genetic programming for evolutionary model discovery, as Tuong was explaining in the talk before me, is because it's great at being able to manipulate these tree structures. With crossover and mutation operators, it's able to take complete sections of these behavior trees and fit them into portions of other trees, and also completely flip around certain sections of trees. And when you do this, what you see is that you can go from having an interaction term to two terms, for example, if this was to represent the utility function, or you could go vice versa. You could have two terms and that could be replaced with an interaction term, for example. So we can very easily manipulate large portions of the search space using genetic programming, which gives us a lot of flexibility that simple calibration does not provide. Parameter calibration by itself does not provide. And the random forest importance analysis, we've tried two different techniques, Gini importance and permutation accuracy importance. I'm not going to get into the details of these equations, but they're the most commonly used techniques for random forest importance analysis. And they basically tell us how important a particular factor is when you're trying to reproduce the fitness data that was produced by the genetic program. So yeah, so with that, I'd like to get into the case study. So in this particular case study, we were looking at what factors affect message prioritization when social media users are under information overload. So for this, we used a multi-action cascade model of conversation. And this is in collaboration with grad students back at the CAS Lab and Bill Rand, who's also speaking right after me. And this model is an information theoretic agent-based model of conversation. Agents have three types of actions they can take. They can decide to initiate conversations, contribute to existing conversations, or share information across conversations. And they're notified by neighbor activity by this tuple of who the influencer is, what conversation have they taken an action on, what the action is, and what content this message, the notification actually contains. And we basically calculate this conditional probability of an agent performing a certain one of these three actions given another agent has performed one of these three actions using a ratio of transfer entropy to entropy, looking at the time series of activity in the event data. And what we see is that given a network of such agents, these agents typically receive more information that they can respond to in a given time step. So we need to simulate these information scaffolds, which basically represent the notification list on Facebook or your Twitter timeline. So we take ideas from theory of extended self and working memory theory, where there's a vast body of literature, and we build what we call an extended working memory. And so this, the mechanism behind this is that when an individual in our system has a certain limited capacity of memory, and which is limited by what we call mmax, and if they were to receive more notifications than they could handle due to increased neighbor activity, then there would be a certain message overflow. We use that message overflow to then calculate what the new memory capacity of the agent is, because in the literature, through analytical studies, we've discovered that we've seen that the amount of the amount of messages that a person is able to process reduces with the magnitude of the message overflow according to a power law. So hence this equation here. And calculating the new memory capacity, which is less than the maximum capacity of an unoverloaded agent, the overloaded agent then loses information. Now, the original model ordered the information received according to how it was, according to recency. So the order in which the messages were received determined the order in which messages were arranged on this array here, which meant that the older a message was, the more likely user was going to drop that message due to information overload. So the newest messages or the more recent messages were kept, were more likely to be responded to when a user was under information overload. However, we decided to take this a step further and look at other factors which could affect this message prioritization. So did the number of unique users on the conversation being mentioned have an effect? Did the number of responses on to that conversation have an effect on prioritization? The global popularity of the conversation initiator, was it a celebrity who first initiated this conversation? Common interests that the person sending the message and the person receiving the message have historically. Historical reciprocity, so the tendency of the receiver to respond to the sender, and global popularity and familiarity of any URLs in the content, and also the expertise that this individual has shown with working with that particular content that was in the message. So did any of these factors actually have an effect on message priority? Was the question that we wanted to ask here. So we set up an evolutionary model discovery experiment with some of the most active Twitter profiles in a cybersecurity interest community. This included cross-platform influence. So we looked at influence from users on GitHub, Reddit, and Twitter that were discussing cybersecurity related issues. And I won't get into too much of the implementation details here, but I will mention that the experiments were run in NetLogo, and evolutionary model discovered the evolution of NetLogo models was performed in Python. And the metric that we used was the root mean squared error to the data of the overall responsiveness. So what was the overall responsiveness in the data versus the simulation? And we calculated that error. And we used the following operators. So plus, minus, multiply, and divide. Yeah, so these are some of the examples of utility functions that were produced. Now, what we see in this particular case study, different from the Anasazi study that Ivan presented earlier, or the Schelling segregation study that Ivan also presented, was that the rules were the best fitting rules were quite simple, which led us to believe that there was a particular factor that was more important in this particular behavior. So looking at the random forest importance analysis results, both techniques agreed that recency was by far the most important factor at play. The initiator's popularity was also quite important. And the interaction of these two factors was also showed to have moderate importance, while the other factors showed to have less importance. And here I'm showing you just the top 10, but due to the nature of the operators, there were hundreds of factors and factor interactions that were generated. What we did next was we tried to find the optimal factor presence. So what you see here is for some of the top factors that were seen, importance decreasing from left to right and top to down, starting with recency. We're comparing for each factor, we're doing Mann-Whitney tests between the presence of a presence level of A versus a presence level of B. And the green squares show you where the man-Whitney test has passed, and the values inside are the p-values. We have a initial significance of 0.05, but this was compared using a Bonferroni correction afterwards. So the green squares show the Bonferroni corrected results. And what we see is that recency is better when it's present positively. So more recent messages are most likely prioritized. Initiator's popularity was better present when it was negative, interestingly. So conversations that were initiated by highly popular users were less likely to be prioritized when a user was under information overload. Conversation size was also had a negative effect, similar to initiator's popularity. We didn't see an exact result for URL popularity, though it seemed to have important interactions with recency and initiator's popularity. Common interest also had a negative presence in the best solutions, and reciprocity had a positive effect. So novel information and reciprocal relationships were preferred when a user was under information overload. Now, we went back and constructed models using these insights. And what we see is that a model where the utility function for prioritization consisted just of recency did perform well compared to some of the other models. But when it was combined with some of the other important factors, moderately important factors with their optimal presence, those more complex models actually outdid the one with pure recency, even though recency was the most important factor. And in this graph, we're looking at the root mean squared error, so lower is better. So finally, to wrap up, the insights with this study is that under information overload, social media users do respond to the most recently received messages, which corresponds to a lot of the some of the literature that's out there regarding recency as well. And we see that conversations by globally popular users are typically deprioritized, which is somewhat related to the friendship paradox as explained in Hodas et al. If you want further information. And we see that there is a slight tendency to prioritize unfamiliar information, which allowed for a sort of novel interaction. And there was at the same time a tendency to prioritize relationships where the agent was sure of a reply. So relationships with high reciprocity were more likely prioritized when a user was under information overload. So some of these results are intuitive, but especially the one where conversations with globally popular users being deprioritized was somewhat of a surprise. Yeah, so this is an example of how evolutionary model discovery can be applied. And with that, I'd like to end my talk, and I'd be happy to answer any questions, but I think we're going to move to the
Yeah, so thanks, Chathika. So we'll do the final kind of content talk really from Bill. We are obviously going to run over. I think we have Firminio's permission to do so. So I hope some of you will be able to stick around for that. So there's one final content talk, and then we'll be into the discussion again.
Sure.
So hopefully everyone can see that and can hear me okay? Okay. Thank you, everyone. Yeah, we are running quite a bit behind, so I'll try and keep this quick. I apologize, apologize, none of us can be there in Milan right now. So I put a picture of Nice, which I took a couple of years ago, closest I could get to Milan. I've never been to Milan, I was looking forward to it. But anyway, let me talk a little bit about inferring complex models of behavior on social media. And I'm actually going to try and tie back into the theory stuff that was presented earlier in the session. And I'm going to do that a little bit by talking about the lure of big data, right? And as Blake kind of sideways mentioned, right, I do think there is still value in big data, right? And I think it is very useful. But I think that, you know, the kind of the lure is this idea that we could take data, create a model, and get output, and we could solve all the world's problems, right, just from that, right? And so we no longer need any kind of theory, right? It's kind of like I think that's actually what Josh is critiquing and Yvonne is critiquing as well, is this idea that we can just do this without any kind of understanding of subject matter expertise, right? And so I feel like that's a problem, right? And I'll give you one quick example, and then we'll dive into what my proposed solution is, right? And this is kind of an example that was drawn from data here in the US, right? Where there's a tool called Predpol that is being widely deployed among local law enforcement agencies that essentially tries to predict where crime is going to happen. And, you know, it does this by taking into account all sorts of criminal data and putting it all together, and then it makes this output. And in fact, the algorithm itself is black box. We're not allowed to see it, right? It's just kind of a proprietary mechanism generated by Predpol, right? Now, they claim, of course, that they don't take race into account. But, you know, what the Predpol targets, the areas that it targets are overwhelmingly black, right, compared to overrepresentative of the population, right? And in fact, if you look at actual estimated drug use of what predictive policing, where they should actually be targeting, we know from anonymous surveys on drug use that in fact most drug use in the United States is in white neighborhoods, right? And so Predpol is kind of not only getting it wrong, but getting it wrong in a really bad way, right? And of course, you can see many other examples of this. Google flu trends and its kind of failure to model data correctly, right? There's a great example in the book Weapons of Mass Destruction by Cathy O'Neill that talks about the fact that teaching tests are often really bad ways to actually grade the teaching evaluations of teachers, right? And or grade the quality of teachers, right? So, you know, what I call this, in fact, the Florence effect, the Florence whale effect of black box modeling. And one of the very first videos to ever go viral, in the sense of going viral, we're talking about back in the 1990s, where you basically had to, like, you know, connect up to your modem to the internet to get it and like download this video that took like, you know, an hour and was very grainy. One of the first videos to ever really go viral on the internet was this video of a whale that beached itself in Florence, Oregon, right? And they weren't sure what to do with it, right? And so they came up with this great idea, hey, we could just blow the whale up, right? And that will kind of move it off the beach and people can go back to enjoying this beach, and rather than, you know, having this stinking whale right there. Well, what in fact happened by using this big tool of explosives, right, was rather than actually successfully moving the whale back into the water, right, the dead carcass of the whale, it exploded the whale all over everyone within like about a quarter-mile radius of the whale. And so now not only does there a smelly whale, but there's lots of it on top of everybody as well, right? And so my problem is that, you know, it's not like black box big data models are deliberately trying to cause these problems, right? It's just that the solutions that we're employing a lot of times when it comes to big data solutions are exacerbating the very problems they try to solve. Not necessarily by creating perverse incentives or anything like that, but they just wind up causing more harm than good in reality. So I proposed in this chapter I wrote for a RAND workshop that became a RAND book that Josh and many others were part of, what I call the theory interpretable models and model interpretable theory principle, that all social science models using big data should be interpretable from a theoretical perspective. They should not be black box, and all social science theories applied to big data should be interpretable from a modeling perspective, i.e. they should not be they should be falsifiable, right? And my point is, and I'm going to talk more about the first half of this today, right? But my point is that we should have some way to take a model that we build and go back to the first principles and understand why it generated the data it did, right? And there is a solution to this, and that solution is the solution we've been talking about this entire workshop, which is kind of this notion of inverse generative social science. sometimes, you know, depending upon the context in which you're using it, data-driven agent-based modeling, right? And of course, traditionally, agent-based models use simple rules derived from theory. Could we use big data in a way to back engineer, to recreate the rules that gave rise to that data that we're seeing? You know, and I have a big vision slide later on, but I really think about this in the kind of notion of a policy flight simulator that two great Johns once talked about, John Holland and John Sturman, right? Which is this idea that we could then build a tool that kind of reflects the reality we see around us and explore policies in a dynamic sense to see how they alter those realities. There's two possible ways to do this. One has been explored by the agent-based modeling community for quite some time, parameter optimization, right? Where you take a preformed structure of a model and you just fit those parameters to the data you see, right? And we've talked a lot about why that is a great solution in many cases, but may lack power in certain environments, right? And you know, I do want to mention one quick tool in this space that I helped work on with Forrest Stonedahl at when he was at Northwestern, now at Augustana, which is called Behavior Search, which is an add-on and now built into the NetLogo agent-based modeling language. And it allows you to quickly do parameter optimization on any agent-based model that you construct to empirical data, right? You have to write the comparison function, all that, but you can do that, right? But today I'm going to focus more on this rule induction notion, right? Which is the particular method of inverse generative social science that I've kind of spent time working on, right? And rule induction is the idea that can we take a big set of data and induce the rules of behavior that agents might be following in this case. And we've applied this to a number of different notions, from social media to marketing promotions. I am a marketing professor, among other things, so I have to work in that space occasionally, right? To a variety of different areas, juries just making decisions, to a variety of other areas that kind of look at information diffusion and how that could be modeled using this approach. And in particular, in particular, we're going to use a tool called Transcissor, which I'll talk about. Just a quick note, this graph looks almost exactly like Chatika's graph that he put up, so I wanted to, kind of emphasize again. I think there is a nice formalized way to do parameter optimization and do these validations. We presented a version of this in the Proceedings of the World Congress on Social Science in 2014, but many people have explored this, and so I think this is a well understood path, and we're kind of building on that to now say, well, what happens if you change the structure of the underlying model? So if you think about parameter optimization as focusing on altering the micro level parameters of the system, does a particular agent have this much desire for alcohol versus that much desire for alcohol? Rule induction and inverse general social science in general is looking at the macro level. What are the exact rules? Like, are social norms important? Are legal rules important? Is my individual predilections important, right? Like, how do we play with those macro level kind of notions, and can we change them up? And in fact, we went all the way to the base. We went to the very beginning, and we started to build upon the Schlesy and Crutchfield notion of epsilon machines, or computational mechanics, or causal state modeling, depending upon who you talk to and when you talk to them, right? And so the idea is that you have a time series of some sort that it was generated by a conditionally stationary stochastic process. In other words, that the current state of the system is dependent upon the last few states, but the overall that model of how it's dependent upon those states does not change over time, right? Conditionally stationary. And then when you explicitly learn the predictive distribution of all the possible outcomes for a particular observed state that we might see, and we iterate all those. We just list them out, enumerate. We enumerate all those possible outcomes, right? So every time we see a certain set of past behavior and we see a certain output, we then group all those together when the output's the same, right? And we kind of try and figure out, are there ways that we can collapse potential outputs given equivalent paths that we've seen in some way, right? And this is Cosma's dissertation work. It's fantastic. He's a great statistician. He shows, in fact, that not only in theory, but in actual practice, the models that get generated are both maximally predictive and minimally complex. In other words, they do the best job of predicting given all the data you've seen, and they are minimally complex, and that the internal states of the agents will be as minimal as possible. The number of states of the agents will be as minimal as possible. So we applied this early on with David Darman, Jared Sylvester, and Michelle Gervon when I was at University of Maryland to predicting whether or not someone's going to tweet, right? So we just look at the past history of how often they're tweeting, and we predict whether they're going to tweet in the future. Here I'm showing the results of our improvement over a null model. The null model just said if people tweeted more than they did in the past versus they didn't tweet, then we predict they tweet in the future. This shows our improvement in that prediction for both a computational state model and a completely black box echo state network, a recurrent neural network that we use as an alternative architecture, right? And as you can see, in most cases, we do as good as the black box model, indicating that these white box rule induction type of methods can do as well as black box methods, right? The other interesting, and just kind of an overall example, or kind of a cherry-picked example, this is Daniel Levy, who's close to the middle on that tweet rate diagram. On average, Daniel tweets 45% of the time, but we were able to predict whether or not they were going to tweet in the next 10 minutes, 95% of the time, roughly 95% of the time, right? So kind of an example of how we're able to improve results. So, I want to take this back. So this is to how we can actually use this. So our initial models were of individuals, but what if we wanted to model all of Twitter? What if we wanted to look at all 15,000, well, not all 15,000. What if we, in an extreme example of all of Twitter, but we had 15,000 users. We knew exactly how they were connected, what their friendship and following networks were. We knew how they tweeted over the span of a 1-year period. We wanted to know, could we predict that activity given these individual level models, right? Given that we have all these different models of agents, can we throw them all together? And this is kind of the classic idea of trying to take individual components that you've seen, and if this were a black box model, and put them together and make an aggregate prediction. And what we found was our model failed horribly, right? And that's important for this, right? Because what we found is that the model failed to account for things like seasonality, right? We were only looking at short-term predictions in the past. It failed to account for the fact that small changes in external social network effects could have a larger effect over time in the system, right, than it did in this particular example. But because we had a white box model, because we had this rule induction model, we were able to go back and diagnose exactly what was wrong with the underlying model. Whereas if we had just trained a neural net to make predictions about what was going to happen in the next time period, we might not have been able to do so, right? And so that's what I'm arguing why, and this kind of tries to point out an example as to how we can diagnose the problem at hand. So I'd like to say we're able to apply the method of rule induction and to social media data and even identify the limitations. And we applied it to a number of other places where we've used it successfully. I think really what I'd like to get to is this vision, right? Which is that if we can truly model individual users fairly well automatically in this way, right, for a particular phenomenon, then we can potentially take those models and embed them in a full simulation of whatever system we are interested in understanding once we start to, get the right phenomenon in hand. This would enable this creation of large-scale data-driven models that could be updated regularly and automatically, and could be used as kind of a policy flight simulator for something like an entire city, right? Like you can imagine that you're modeling the city and examining what's going on and having it being updated on a regular basis according to streaming data sets that are out there, and noting changes in behavior, noting changes in activities, right? It's the closest you can get to Isaac Asimov's notion of psychohistory in my mind, right? You're kind of getting to this idea of being able to produce large-scale models of social behavior. Now, we're not anywhere near that, right? I want to make that clear, right? But that is the vision that I am at least trying to work to. So with that, if there's any questions, I'm happy to take them. By the way, if you're interested in general in agent-based modeling and these kind of concepts, I touch upon them briefly in my Complexity Explorer course that I offer online via the Santa Fe Institute. Feel free to take it out. It's been taken over in some parts by Ana Maria Barea, who's a great former postdoc of mine who's been teaching it for a while, and she's doing a great job. So thanks, everyone, and I'll end there.
Thank you, Bill. Thanks very much. So yeah, we'll throw it open now to discussion. I think if you've got any questions, just indicate in the chat. You don't have to write your question there. Just indicate you've got a question, and then we'll open your mic.
see Sarah has a question. Oh, that's all right. See, Matt Kohler has joined the proceedings. Excellent. Robin, are Doyne and Blake giving another round of reactions?
Doyne's had to go to an urgent video call.
Okay.
Blake's on the chat, but he's
Okay.
he's had to give up his
video thing. Okay.
his video, yeah. So we don't get the formal discussion this time. But yeah, open it up to anyone who wants to.
Please.
While we're doing that, Blake did mention that, he asked if we push the limits of big data technologies and things like that. And I think the answer is no, of course not, right? Like, we need to keep trying some of this stuff. And I think there's probably better and different ways to approach it than what we did, right? And Blake now is asking, how does the GP and Shalizi stuff compare, right? And I think that's a great question. And I've worked with Chataka on the work he's doing, so I'm not unaware of that work, right? And I think that really, this kind of brings up a bigger question that I think is part of the agenda of the iGSS in general, that a group of us who were at a meeting in Virginia in January that we helped organize discuss. But what is the appropriate method to use at the right time, right? And so the causal state modeling stuff that I discussed, that's really good when you have data that has a small alphabet. You can only do a couple of things, right? Like tweet or not tweet, or in the marketing stuff we looked at, it was like respond to email versus web versus mobile app, right? There were like 7 technologies, right? And it's high frequency. There's a lot of actions that are happening, right? And it's time series, right? Which is what we are looking at in that case. And that it works very well in that case. In any other case, it doesn't work that well, right? The GP stuff is kind of a more general language in many respects, but even there, right? Like, it does face a computational limit once you start to really explode the number of primitive operators that are being looked at, right? And Tuong and Robin, I don't know if you want to comment a little bit about the approaches you're using and when they're appropriate.
Can I interject a point, Bill? Great talk, as always. Here, I think this does raise this question about prediction and explanation. I mean, I was also kind of thinking of Jim Crutchfield's work when I made my kind of elliptical point about the steam engine. I mean, I think if it's just about predicting, then you don't care if it's a black box. I just care about the prediction. But if you care about explaining, generating, and revealing operative rules and mechanisms, then I think the sort of work Chataka showed is much more compelling. So it's really, I think part of it is, what are you trying to do? I mean, if you're just trying to predict, then, the finance world is, going crazy with this stuff, as I think Blake would agree. But I mean, if we're trying to get at underlying human rules, then I don't think that alone is very revealing.
There's a
Can
question.
I add one quick thing? Sorry.
I mean, you might do both. You might get both, as Doyne was saying. But anyway, Chataka, please.
Yeah, I was just going to add to what Bill said. So the problem that the GP system does run into when you do a complexity analysis on this is that it's actually the depth of the decision trees that are produced that have the highest hit on computability. Yeah, so the deeper your decision trees are, the more computation you have to do versus the number of agents or the number of factors even that you include.
Yeah. Thanks, Chatik. And there's a question in the chat from Blake around, do any of these systems work hard or not hard to maintain diversity in the populations?
Excellent question.
For the multi-objective formulations or multi-criteria formulations, most of those algorithms have mechanisms that will try to promote diversity, at least in the criteria. So they'll try to get some kind of even representation of the Pareto front in criteria space. There's other methods that also do it in the design space. So, you know, niching, you know, going back to some of the work in the kind of 80s and 90s on in the genetic algorithms field. So we did a study with the theory of planned behavior where we explicitly put in a fitness sharing that was explicitly looking for diversity in the parameter space of a theory of planned behavior model. So it kind of depends. Most of the multi-criteria algorithms come with diversity promotion as a standard kind of bit of them. For some of the others, it is possible to lose diversity. It kind of depends what's in there.
Yeah, I would add on, you know, like, in fact, it's interesting, both the you know, it's very necessary in the GP type of solutions to do this kind of stuff. The interesting thing about the causal state modeling solution, right, is that really, given a particular data series or time series, we're only getting one model, right? Like, there's only one possible model. It's deterministic given the data that we've seen, right? Which is an interesting answer. And it kind of ties back into what Josh is talking about prediction versus interpretability. These models are interpretable in some respects, right? But they're not, you have to spend effort to interpret them, right? Whereas when you create the primitives, right, that you're talking about, that are used in the Chataka type models and the alcohol models, you're building up from the subject matter expertise to that model, right? Whereas here, I'm showing a method by which you can use a machine learning approach to, you know, impute the best possible fit to the data. And then you have to kind of tie the resultant white box kind of solution to the theory that you have about how people behave in that space, right? And so it's kind of top down versus the bottom up type of approach might be where it's kind of where does the subject matter expertise come from, right? Does it come at the bottom and create the model, or does it come at the end after you've created the model and interpret the model?
But Bill, would you agree though that Cosma's approach doesn't return rules in the sense that Chataka's model does?
It returns. So the way we use them, right, maybe is a way to put it, it returns these rules of how agents move from one state to another, right? It's then up to the social scientists to interpret what that kind of transition probability means.
But they're just
right?
numbers. They're just numbers.
They're numbers.
Right?
They're just numbers. Yep.
Right.
Yeah. Yeah, I guess it depends on what you mean by rules.
Yeah, I mean the sort of things that Yvonne and Chataka showed, but I'm all for big data. I just think it's useful to, when you use it as the target, then of course it's indispensable.
Yeah.
Right.
Yeah, in that social roles model that Twong showed, I think there were 14 non-dominated models, candidate models, and I think 3. So then when we had that kind of iterative debate with the domain expert, I think at the first iteration, none were considered credible. Second time round, none. And the third time round, we found 3. And when Twong, he set out those kind of 3 criteria for theoretical credibility, they were emergent criteria. So we didn't, the domain expert was making holistic judgments, and then we tried to infer a set of criteria afterwards. So we didn't, in that study, we weren't trying to impose what the dimensions of theoretical meaningfulness or credibility were, because I don't think we knew. You know, we needed the expert who could, you know, sometimes, yeah, it was obvious, but in some cases it was more nuanced, and they were kind of bringing in domain expertise that we hadn't been able to encode in the grammar. Yeah, so it'd be really nice if we could, and we honed the grammar, but still in that third iteration of grammar, we've still got the majority of structures are being rejected by the domain expert.
Yeah,
so,
I think I would say, just quickly, I would say that I think there's a ripe opportunity to work from both sides, right? Like, is there a way, like, to work from the data down and from the subject matter expertise up at the same point and see what you give up in each situation, right?
Yes.
There's some sort of predictability, interpretability trade-off there, right? And at what point is there a middle ground that's best? Right? Anyway, sorry.
So just a quick point, if I may. So in our way of looking at this, we use both, right? So we have a method we call agent-based modeling canvas, when we put the experts for certain phenomena, and we tackle it from different point of view: policy, politics, social, anthropological, whatever we think is important. And then we distill from them those factors. Those are the building blocks that then get recombined. But we also throw some building blocks that come straight from data, right? So we're perfectly fine looking at correlations in the data that we find important and putting that as a building block, and then letting the GP to recombine them and come up with some results that work. So we use both.
Can I ask Chadika a question? So,
Sure. Yeah.
so in a lot of the literature on, so in connection with Agent Zero and this whole literature on fear versus deliberation, there's a lot of psychological work showing that under circumstances of stress, the fear module dominates the reason module. And in situations of low stress, deliberation can actually rule the day. And your overload work sounded like very analogous to that. And I wonder whether it would be enjoyable or possibly even productive to think about doing more along those lines, where there's an agent in the Agent Zero constellation, perhaps, or some other constellation where there's an environment that could be stressful and overloading, and another environment that could be less so, and the agent changes his priorities. One priority is just survive, and it's all about fear, and another is do something a little more reasoned, deliberative, rational. Just a thought. I mean, I thought it was fascinating work. I just wondered whether it might apply in an area like that.
I think that's really interesting. I never thought about it that way. But so from what you're saying, the degree of fear could be what drives the loss of rational units of decision making, for example.
Yeah.
And
under overload, then you revert to the more primal of your modules. Right.
Interesting. Yeah. Of course, I think we need a different case study to look at.
Oh, of course.
Yeah.
I mean, voting might be a good one. Voting for fearmongers is the one that occurs to me. But
yeah, that is very interesting. I never thought about that.
Point from Flaminio there, and we need models that look at the co-evolution of context and agent behavior. Perhaps a taxonomy could be helpful.
Yes, perhaps in the line of Josh, for us to probably need to work a little bit of some taxonomies in which we can classify types of environment and type of agent behavior and this kind of co-evolution in the line of thought that could be probably helpful.
Right. Yeah, I agree with that.
So whenever we speak to someone non-ABM and non-complexity kind of researchers, and it happened this week when Anima Anand Kumar gave a brilliant talk about the frontiers of artificial intelligence and the role of simulation in training algorithms where data are not available, and with the example of driverless cars and etc. So, and when I ask her about what do you expect from our community, to contribute to, and he said, well, I will expect something like a taxonomy in which we know very well that at some circumstances, some kind of environment, some kind of context, humans typically behave in that kind of way and interact in that kind of way that produce that kind of outcomes. And indeed, it's something a little bit missing in today. Yeah.
Mm-hmm.
Yeah, I agree.
Yeah, I agree. In fact, we did, Josh alluded to it, and the website is still up if anybody wants to check it out. I will throw it in the chat, iGSSworkshop.org, where we held one of the first workshops on this topic. And one of the things I was hoping to come out of that was actually a set of documents that might contain like a taxonomy of the different ways you could have these coevolutionary behaviors, and what are the kinds of different ways to apply iGSS. And unfortunately, we had that conference, and like, a month later, COVID hit, and like everything got so I still have it on my list of things. I still have all my notes typed up carefully about what we discussed. I plan to write up into kind of the beginnings of a manuscript for that space, and circulate it among the people who were at that meeting.
Yeah.
There, Chadwick put it in the chat for me, so it's there.
Yeah.
But the talks, and we have recordings of a bunch of the talks if people are interested in more comments on that workshop.
I think we'll move on to the kind of penultimate bit, which was the toolkits that have been developed, just to introduce you to what's available. Chathika and Twong, I'll let you organise yourselves to kind of show us what's been developed.
Sure, thanks, Robin. Let me share my screen. All right, hopefully you can see this. Yeah, so I'm going to talk about the evolutionary model discovery tool, which is a open source Python project. And you can easily install this just by pip install evolutionary model discovery. So as we've been explaining, this package allows you to explore generative mechanisms for agent-based models. And for this particular package, we're looking at NetLogo models and evolving NetLogo code with the genetic program, as I described before. So the solution is able to automatically generate NetLogo syntax. And then it also is able to apply the random forest importance analysis, as I explained previously, in order to give you an idea of what the most important factors are, quantify that for you. And the package, the project is available using the QR code there, or you can get the source and documentation at those two links. And yeah, so I think I went through this architecture previously, but just to recap very quickly, the system works by taking an agent-based model and a set of hypothesized factors of decision making, running a genetic program on it to match macro patterns in data, and then training a random forest regressor and performing factor importance assessment on the produced data. And then you can identify the optimal factor presence for those most important factors using evolutionary model discovery. And how it works is, I've tried to make this as usable as possible, but I'm always happy for feedback. Matt Kohler's team has been very helpful in giving me feedback recently regarding some of the newer versions of the software. Yeah, so you basically define your EMD entry point using a annotation as a NetLogo comment. So you can do all of this in your NetLogo code, so you can make sure that it's compilable with NetLogo. And as soon as you put an @EMD, the Python EMD package recognizes that this is a EMD entry point, and you have to say @evolve next line. And you can provide a file where, NLS file, where you have your factors set up, and you have to specify a return type. So this particular line will return a custom type, float. And then you have to define your factors, which are essentially NetLogo reporters. And these NetLogo reporters must compile within your NetLogo code. And you specify a factor using the @factor tag, and provide the return type, and then all different parameter types depending on how many parameters you have. And again, this is a strongly typed system, so these types have to match. And you can also similarly provide your operators by saying @operator and providing the return types and the parameter types accordingly. Yeah, so the next step is to write your evolutionary model discovery code in Python. So you can simply import the package, write up some setup commands, provide the path to your model, provide which measurements, a list of measurements, which you would like to take. In this instance, I'm evolving the Schelling segregation model, which Josh and Ivan talked about earlier. And then you create the evolution model discovery object. You also need to provide a objective function for the genetic program, which is able to return a particular metric. And you set that to your experiment. And you're able to specify hyperparameters for the genetic search. And then you just say evolve, and the genetic program is able to evolve new NetLogo models for you. The random forest importance analysis can then will then provide you a calculator, which allows you to calculate both the Gini importances and the permutation accuracy importances. So below is an example of the permutation accuracy importances for the Schelling segregation experiment, which we were talking about earlier. And in order to find the optimal factor presence, you can also use evolution model discovery, this evolution model discovery package to calculate the optimal factor presences as well. We can calculate optimal factor, optimal presence factor. And just an example of why this helps. So we were talking about the Schelling segregation model previously. And what we see is certain factors by themselves produce very highly integrated patterns. And two of the most important factors together still produces a highly integrated pattern with globs of unpopulated areas. But the interesting thing is that when we combine, when we have more complex rules, we finally find integrated and segregated mixed patterns. In this case, for the Schelling segregation model, more complex patterns that actually match the real world. And this discovery of these sort of complex rules might have not been possible without doing this sort of exhaustive search and automating this exhaustive search. So that's the advantage of using the evolution model discovery toolkit. And with that, I'd like to hand it off to Tuong so he can talk about his work.
We can't hear you, Tuong.
All right. Sorry. Yeah, I'm going to go through this really quickly. One of the tool that we build is called the MBSSM architecture. And when we're building this, we are already thinking about the requirements that you need to be supporting the individual mechanism-based social theory. You need to be able to combining different theory together, and then you can extend and maintain it easily. So the source code is available online, and then we also included a very simple example of scaling segregation that just bring out some result like this on the screen. And then this is an example of how you're using the framework. So basically, the architecture. So basically, the architecture is will stay at the core, and you will keep extending it by adding the relevant class and relevant theory that you want. So the idea is that by keeping extending this, you can build a library of theory of mechanism that later we can combine together. And the nice thing is that you build on the same core, so we can actually working within the core and don't have to worry about the interaction between the theory. Talking about the tool set, our models is in Repass HPC, it's C++, and then we build for parameter calibration, we are custom built some the R code for approximate Bayesian computation, rejection sampling. And then when we do the model discovery, we're using in the first instance of the social norms model, we use ECJ. But later on, we switched to Pony GE2 developed by Dublin University College Dublin. And the nice thing about this is that the grammatical evolution. And I want to stress it again, because for using the grammar, what you can do is that you can incorporate the knowledge of the domain expert within the grammar. So as Robin said, we iterate this grammar over a few iterations to achieve this. And let's say, for example, you can see that in drone load, they're using variable 1 and variable 0, which is the involvement, role involvement, and your role status. But for example, in role strain, we restrict it and say role strain, you only allowed to use role load and role incongruent. So you somewhat can use the construct or kind of taxonomy and don't allow your GP to go haywire and do crazy things. And I think this is really helpful. And this is just some screenshot of what I use. That's it. Thank you.
Thanks very much, Tuong. So I'll hand over now to Josh. A mere 45 minutes later than planned for.
Oh, that's great. That's great.
For some final reflections.
Well, first, I thank everybody and the participants and co-presenters. I mean, I'm just really thrilled about everything that's going on. So I hope people are as excited as I am about this entire line of work. I mean, I think it could really be a watershed for agent-based modeling, both as a predictive tool, as an explanatory tool. Of course, you know, we use big data, machine learning, everything we can, but I think it'll give us, you know, very, very new forms of insight. I think Chatika's, what he just showed on the Schelling model is just a marvelous example. So I'm very excited about that. The only kind of science point that occurs to me, and I thought everybody's talks were great. Robin, I thought your presentation of the frameworks was great. Same for Tuong, beautiful work, as you know. So I think you're really at the forefront. You and Chatika and others are really at the forefront of this I think revolutionary move. So I'm very excited about that. I don't know if Yvonne's still on the call, but I you know, of course, I also love all the deep agent work, and I think that's also a huge axis of advance. I do like this idea of growing. Yes, there's real data we could try to generate, but I also love the idea of doing other exercises like the Schelling exercise, where you take a kind of seminal agent-based model and see if there are other ways to do that. I mean, not because you know, just because it's on my mind. The Sugarscape model would be an example. I mean, we had this silly gradient rule where they look for the better sugar and end up on the peaks. But if you just said, find ways to end up on the peaks, you might get all kinds of ways to end up on the peaks. I mean, random movement, but, you know, follow the fat guy or something. I don't know. I mean, not that there's anything wrong with that. But the point is, we could play a lot of interesting games with classical agent models where the data is very clear, where in the real world, the data is never really perfectly clean. So just as a proof of the method, we might take those as targets. The other one is the business about causes, something generating something in a model and other things causing things in the real world. I think this is a little problematic. I mean, you could say A, in the model, A generates B, all right? I don't think that means that there's a physical analog of A that causes the physical analog of B. And in a lot of science, there aren't physical analogs for important explanatory components. In quantum theory, the psi function is an imaginary, it's a function of a complex variable. So I'm not sure, I think we need to think carefully about the relationship between generated in a model and caused in the world. But I think that's more on the philosophical end. But yeah, I mean, I'm just thrilled about everything that's going on. I thought the presentations were spectacular. I think there's a million things to study and a million deep, fundamental, foundational, philosophical questions to grapple with. So to my mind, what could be better? I'm thrilled with the whole thing, and I thank everyone. And you know, including the participants and Flaminio, of course, first and foremost, for organizing this great event. And yeah, I look forward to tomorrow.
Indeed. Yes, looking forward to your lecture tomorrow, Josh.
Oh, thank you. I'm very honored to be giving that lecture, so I look forward to it too.
And thank you. I just want to thank you know, on behalf of the organisers, everybody, and my co-organisers, and all the participants, particularly those who stayed on for the extended duration. So thank you very much indeed. And
yes.
yeah, let's keep up the conversation. I think it is an exciting area. Brilliant.
Thank you. Thank you all.
Thank you. Thank you, everybody.
Thank you.
Thank you.
Gus from Milan here.
Yes.
Thank you, everybody. Take care.